I was particularly fascinated by this book that you wrote in English 2 years ago, because it shows you the discovery process of scientists. So there are many popular science books. I wrote some of them too, but they often tell you about the outcome of scientific inquiry. And sometimes, for example, some of the modern physics results are very sophisticated, both in terms of mathematics used and experiments that involve the very complicated. And so often readers just have to accept what we say as a fact. But your book is very different in the sense that it shows you how scientists discovers. And so I thought first I would like to ask you, so how you started your class in Harvard 10 years ago. What was your motivation of starting this class?
Yes, thank you for asking. I think that, well, first of all, the motivation for the class actually comes from my wife, Afarin, who is actually here, and she suggested to me to teach a course which is close to my heart for the freshmen. And I felt that trying to teach physics in a way that is not necessarily about physics per se, but about ideas surrounding physics, like mathematics and simple ideas, would be more important for people who are not necessarily going to become physicists, but want to know what it is about. Mm-hmm. And I felt that that's a piece that's not necessarily, when we teach courses at Harvard or other places, we usually teach them the full thing or nothing. And we don't have a kind of a introduction to what it might be if they kind of see it in a simpler, gentler way. Now, related to the point that you mentioned, is that most of the time, I think that the public kind of imagines knowledge, science, and scientists is accumulation of knowledge. And actually, even though that's partly true, but even what's more true is not scientific knowledge gathering or like a stamp collection. That's not so much what it is, but the method that scientists think. Right. Mm-hmm. That too, for scientists, is much more valuable than collecting knowledge. Knowing a lot of things is less interesting to us than the methodology of thinking about things. Mm-hmm. So I felt that to try to bring that to the public without saying, okay, there's black hole, there's early universes this way, these are just like stories for the public. I felt that it'd be good for them they wouldn't get to the methodology of how scientists actually feel and what they do. So I try to find puzzles which illustrate physical principles and gets them into the act like they are doing it, like what we do in science. And they do this kind of puzzles and they give an introduction to some pieces of fundamental laws. Not all the fundamental laws, but that was not my aim. The aim was to try to get the ideology of how the scientist thinks. And one more thing is that one might think that puzzles are kind of simple. These are so simple, but scientists must surely be doing very difficult puzzles and much more than this and much more complicated things. But actually the truth is the complications that they have relative to what they know is like these puzzles. It is very similar to these puzzles. The spirit is similar. And when we sit down and try to solve science questions, as you very well know, Hiroshi, is to just try to use simple ideas, just like simple ideas which lead to the solution to these puzzles.
Right. Yeah. So when I was reading this book, one thing that struck me was that how this process of formulating a puzzle and answering this actually accurately reflect my daily life. That is, as a researcher. Many things that, so I have, as I mentioned, I collaborated with 28 papers with you, and I learned a lot from you.
Oh, from you.
But one thing that I am constantly amazed about you is how, so often when we start doing research, we have like some vague idea and wanted to understand certain things, and there is some vague puzzle. So how you come up with a very sort of sharp question that sort of encapsulate the vague impression we have, which demand sharp answers. And then that becomes the core of solid knowledge from which we build. So this process is very mysterious. And so this is one of the things I try to emulate by working with you, and have not succeeded very well.
You're too humble, Hiroshi. It's the other way. I mean, I've learned a lot by collaborating with you, and it has been among the most pleasurable works I've done is works that I've done with you. I think that though you put your finger on exactly the right point, namely trying to get to the crux of the matter in a question is the key. And to understand, to make progress, to solving a problem, it's very difficult sounding, for example, you talk about the expansion of the universe, there are all these stars and galaxies and this and that. But if you reduce it to simple ideas like, oh, there's just matter here, they're almost uniform and so you simplify the ideas and say, what is the crux of it? Oh, it's expanding. Oh, why is it expanding? So you simplify the question without getting bogged down too many details. Similar to these simple puzzles. And I think that's one of the things that scientists often say, that we don't understand why the universe is comprehensible. At some level, it shouldn't be this comprehensible. And these are the reason, deep reason we still perhaps don't understand why, but it always boils down to getting a simple point, just like the simple puzzles.
Right. Yes, indeed, it's very mysterious why human has succeeded to understand and decipher the universe so much. The evolution has not prepared us to do that.
We don't know why, but
yeah.
we are lucky.
Yeah, so maybe for the benefit of the audience, perhaps we can go back to some of the puzzles that you mentioned and discuss the context of physics and mathematics in those puzzles. One thing, for example, I particularly liked your puzzle, the first puzzle about colored water, because it's sort of encapsulates the idea of symmetry and conservation law so very well. One of the things, when we talk about symmetries and conservation, we often quote Emmy Noether, who was a distinguished mathematician in the early 20th century. And she discovered that whenever you have symmetry, there is a conservation law. When you have a conservation law, there is a symmetry. Symmetry and conservation go one by one. So that's a very abstract concept. But your example is very core of this idea, and it's very close to the original idea of the proof of Noether's theorem, but in a very simple everyday context.
Yes. I felt that this is actually illustrates the idea without getting to the detail of the math, which is, as you said, very non-trivial. And as you mentioned, this Noether's theorem, which we call, says something really surprising. For example, people who are not physicists, everybody has heard about energy and energy conservation in the sense that energy doesn't get lost. They get transformed from one form to the other. And people also know that if something happens today, if you repeat it tomorrow, the same thing will happen. The same thing will happen the day after tomorrow, because it doesn't matter when you do something. So this is what we call time translation symmetry. You can do today, tomorrow, the day after, and so on. The fact that these two things are related is bizarre. And so that theorem that Noether had was the symmetry of shifting the time to future or past, not mattering, is the same as conservation of energy, that the energy doesn't get lost, is amazing. And yes, I agree. These are among the most beautiful statements.
Right. And also, I like your puzzle about the highway, making the shortest highway connecting 4 points. And this illustrates the following idea of the idea of symmetry breaking, that somehow laws of nature tend to be simple, but its manifestation in nature can be complicated. And actually, here I would like to quote the famous word by Yoichiro Nambu, who came up with the idea of spontaneous symmetry breaking in the context of quantum field theory, and that's his citation for Nobel Prize. And he says that the laws of nature are simple, but our world is not boring. And that's a wonderful combination of both. And I think that, but highway example is very nice in a sense that this is something you can understand, by elementary mathematics, but still demonstrates the fact that even though the requirement is simple, just to find the shortest path, but then the manifestation can be complicated. So there are many things in nature where laws of nature make simple requirement, but its manifestation, for example, our world is not boring. And so that's a very interesting illustration. So I think some of the problems were known, but somehow you found connection so that was how you constructed your Harvard course?
Yes, exactly. So just going back to your spontaneous symmetry breaking example. So indeed, like the example of the highway, there are many beautiful phenomena in physics which illustrate the breaking of the symmetry. And one of them is, for example, superconductors. I mean, these amazing phenomena, like you have for some material at low temperatures, there is no resistivity on the circuit at all. Sounds completely impossible, but it's actually true. Again, goes back to spontaneous symmetry breaking. So whenever you have these kind of phenomena, which you break something interesting replaces it. It's not like a bad thing. It actually is a great thing, like the superconductor, for example. And so indeed, that's the idea about this particular one. And more generally, my interest was, so I should perhaps say how it led me to make this course. From childhood, I was exposed to puzzles. I loved math. And so I would be hearing puzzles from my friends, from relatives, from classrooms, and so on. And I loved to solve puzzles. And then later on, as I grew up, I became more interested in science and physics. And I saw connections between my favorite things about puzzles and what I was learning in the laws of physics. And I say, oh, this is just that law, and this is the kind of thing of that law. And I tried to connect what I knew about the puzzles to what I was learning in physics. And I found that almost everything I'm learning in physics has a simple model, as a simple puzzle, illustrating it. So I said, the core is what we are interested in. You see, in science, we are interested in core of the ideas. We don't care to get details of complicated math formulas. The formulas and all that for us is just to make sure that we understood the subject. And the core thing is what we're after. Just like the core of a puzzle, which once you get it, the rest you don't care about, because the moment of understanding is what you're looking for. And that's what scientists are aiming for. And that's illustrated by puzzles and the crux of it.
Yes. Yeah, so often we say that we are trying to solve the puzzle of the universe, but when we say that, the word puzzle is used as a metaphor. But you say that it's actually the process that we attack those problems.
Exactly,
yeah.
Yes.
So we have a few questions from the audience, and a couple of them actually is following up on this conversation. So I would like to raise it. So one is our audience asks that how you try to come up with new ideas and what helps to come up with the idea. And the other question is more to the point on how you identify puzzles, specific puzzle in the program that you're trying to solve. I think that we often say that if we can formulate good programs, we have solved the half of the problem.
Yes.
So the half of the things that we need to do is to confront some vague problems and try to come up with a sharp answer. And I think the question from the audience is, how do you do that? Yes. And in fact, I would like to know that. How do you do that?
Well, I thank you. But I think that for me, a philosophical view of science is important. So I will give you an illustration. Right. You see, science is, to me, very much like an art. And the way an artist views what they are doing is very similar to what I feel, what we are doing as scientists when we approach nature. We look at aspects of it which are not necessarily provable, but something more aesthetics, like beauty. Right. We often think about, is this a good answer? Is it pretty? Hardy said something, a mathematician said something very nice about math, said, there is no permanent place for ugly mathematics. You always have to have a beautiful thing for it to be kept. This is true also for science. We look for beautiful things. We look for simple but beautiful things. And so this sense of aesthetics leads to no idea. So I will give you an illustration. Suppose you know some subject in science, let me call it that subject A. And then you have another subject which you call B. So there's this A here, and then there's this B here. And after studying these two independent things, you find the bridge between them. A is related to B. A has nothing directly to do with B, but you find the bridge. So you see, A has something to do with B. Interesting. So this is a line. And then somebody says, oh, A has a cousin, A prime. Oh, A has a cousin, A prime. And then you look for the right-hand side. Where's the cousin of B? This is nothing to do with science. This is aesthetics. It's just not pretty to have A connected to the B and A having a cousin A prime and B has no cousin. So you look for a cousin for B. So that idea becomes a new idea. You look for the idea, B prime, and then you try to connect with a bridge. Then you say there must be a B prime and there must be a bridge between them because otherwise this looks ugly.
Right.
So this aesthetic question leads to a question that actually leads to new ideas in science, which a priori has nothing to do with science. This aesthetics is, in many cases, has led for me to many of the work I do has been driven by aesthetics of this type.
Right. Yeah. So this is one of the mysterious things. Why beauty leads to truth? And in mathematics, it's sort of understandable because they are looking for some beautiful structure. And the proof, if you have a good formulation of the problem in mathematics, well, it should have a beautiful theorem, a beautiful proof. But in natural sciences, why do you think that beauty leads to truth?
I don't know why. These are beautiful questions. I don't know the answer. I just know that this is what I do and this has been useful for my work. But why it should have been useful, I don't know. So nature likes to be beautiful, but you could say, what does beauty mean even? So in some sense, the thing that works is what we are somehow identify with beautiful. So I'll give you an example. Some people say, Einstein's theory is much more beautiful than Newton's theory, right, but it's much more complicated. Yes. So if somebody gives the Newton's equations to a computer, it's immediately solved. If you give Einstein's equation to computer smoke comes out of computer and nothing gets solved. It's too complicated. You simplify this and so on. So naively, you might think Einstein's theory is much more ugly than Newton's theory, but that's not true. So the way we think about it and what leads to thinking that Einstein's theory is simpler, despite the fact that mathematically is for sure more complicated, is a judgment of aesthetics. Right. And how we come up with that judgment is, I think, the way we have been growing to learn about science. So I think centuries of understanding has led it. For example, unification of forces. We want all the forces to be just one force. Why? It's simpler. Mm-hmm. It'd be nice if the universe is simpler. Why should it be? We don't know, but it seems like it is. So there's no good reason why, if you have 5 different facts, they get connected to one fact. It could have been no connection between them, but experience has shown they are connection and we are lucky. And so simplicity has been driving these kind of things in science. And so therefore aesthetics seems to be playing a role in actually discovering the truth for reasons we don't have a good explanation.
Yeah, so this is one of the mysterious things that we have no explanation. But based on my experience and your experience, it seems like in addition to logic, there is a place for aesthetic to play a role in research. And there is also a place for intuition. Yes. And intuition is also something very mysterious. And when I work with you, for example, there is a moment when you just say, the answer, this is the answer. And you just write down the answer. Why? Why? Somehow you know the answer intuitively. Well, and then we have to work very hard afterwards, yes, to come up with.
Kind. I think like maybe 10 times I get the wrong answer and then maybe the 11th one is correct. But yes,
but occasionally one count.
occasionally I get the right answer. Yes, but I think that actually, to be honest, the process of what goes on in scientists' mind and in particular my own, I don't fully understand. So if you ask me how the process led to that, I don't have a good answer. Mm-hmm. Many of the thoughts I have come when I'm sleeping, for example, mm-hmm. has nothing to do with the conscious calculation of anything. So I cannot have a good explanation. But what I can say is that thinking about the problem continuously mm-hmm. has often led to these insights, which I don't know where it came from. But I know that without hard thinking, those things would not come either. Mm-hmm. So a prerequisite for these ideas seems to be really hard work. Mm-hmm. But there's no systematics of where that hard work translated to that idea. It just comes out at somewhere, nowhere expected.
So I just need to work harder to get to the stage where it comes naturally, intuitively or something.
You know already more than I do. So.
Yeah. So, but I found your book, structure of your book very interesting. Well, there are some duality in the structure of your books. For example, you have, in the middle of your book, you have a section about intuitive physics or physics intuition, and also intuitive mathematics, intuition of mathematics. And then in the next couple of chapters, you have counterintuitive thing about the mathematics and counterintuitive thing about physics. So you start with some intuitive things that you can understand, but then you say, well, look, sometimes your intuition fails. And then in some sense, you need to update your intuition. That's, and then you have sort of even sharper intuition. So I think that, but also there is a distinction between physics and mathematics, and this is one of the things that one of the audience asked about. Yes, please.
So this thing about the thing you just mentioned about the A versus anti-A, your intuition, non-intuitive, and so on, is part of the way we have learned. At least my impression of what we are learning in physics is that the truth is not one thing. It's not. In other words, there is a truth, but the angle that you look at it are different angles, and the angles could be contradictory looking. And so if you just have the whole truth, and if you look at it only from one viewpoint, you miss the truth, even though you're looking at the truth, because there are other angles which look opposite views, which look completely different answers coming out. So this picture that you have, our understanding is one thing, is not really what it is, I think. I think there are patches of understanding which fit together, and these patches don't look compatible. They look kind of contradictory occasionally, or in some tension. And it's precisely because of this tension that it gives you richness to that reality.
So by trying to resolve that tension, you get to the even sort of higher level of understanding.
It looks like a beautiful musical piece where you need a little tension and this resolution to make the music hang together. This is similar, I feel, about these counterpoints in science, which look like they're almost saying opposite things, but they nevertheless are barely fitting together in a beautiful, consistent way, and they reinforce each other.
Right. Yeah, so I think that we often, in our research, we often have this point where we thought we understand, and then we build some intuition with it. And then we discover that there are some things that our understanding does not work out. And then we try to resolve it, and then we get to the even higher point of understanding. And so this is very interesting. Your last example was also interesting illustration of counterintuitive fact that you try to divide some geometric object, and then if you divide with one line, you have two. If you have two, you have four. Well, I thought we discovered the truth. But then if you look closer and if you gather more evidences, you discover that the laws are not simple. But in the end, actually, you have a much more interesting formula that so in some sense, if you understand the whole thing, it becomes intuitive again. It's become part of your intuition.
Exactly. So by looking at the problem enough of it, by finding our own mistakes, correcting it, we get a better picture, better understanding until the next question comes up and so forth. And I think that's the process. Of course, the formula I showed at the end of the puzzle was a math problem. So that ended. Just like, for example, Pythagorean theorem, you prove it, and it's finished forever. There's no doubt. We are not coming back to that. So that's a bit of a difference between physics and mathematics, which I think we can come to. But I think that physics never ends, unlike mathematics, which ends. In fact, we know a lot about physics. We know about the reality and so forth. But I still believe that today, all the laws of physics that we know are some kind of an approximation to the actual truth. I don't think any of the laws of physics we know today are exactly right. Unlike the math, where you do Pythagorean theorem, you prove that it's finished, you're done. So physics is a bit different. So we are always looking for the next level of truth. It's not the end, never.
Right. Yeah. So, 100 years ago, David Hilbert posed 23 problems at International Congress of Mathematics in 1900, I think. And one of the problems was actually find axiom of physics. And that one, I think, was a wrong question to pose, because physics is not a complete subject yet, and it's not like you can formulate axiom for physics.
Yes, that Hilbert's questions, one of them actually led, probably related to this, to the Gödel's incompleteness theorem, which is perhaps not unrelated to the fact that no axiomatic system can describe reality completely, because
even in some mathematical word.
Even in some mathematical word.
Yes. Yeah. So may I come back to this question posed by the audience? One of the audience asked, So in your book, actually, you have a section, you have a chapter about physics, and problem taken from physics, and many of the puzzles in that chapters are about motivated by physics or explain some ideas in physics. And then there are also chapters about mathematics, counterintuitive mathematics and intuitive mathematics. So one of the audience wanted to ask you, what do you think is the difference between physicists and mathematicians in terms of their way of thinking, the approach to the puzzle and programs?
This is a very good question. I think physicists need to feel things. Like, for example, you say there's this particle colliding with the other one, and one of them pushes it this way, and there's this other force, and so on. You, as a physicist, you put yourself in the place of that particle. You feel like you're getting that other force, and so on. You feel like that. You have some kind of an intuition. A mathematician typically looks at the structure of the thing. So it's a bit different. You look at the relation between things, the definition of things, and how they hang together. Whereas physicists kind of doesn't have an axiomatic structure, and that's not what it's saying, but the relation between different facts, different things that we know, how do they fit together? In physics, it's less hierarchical. We don't try to put one fact as more important than the other one. We think the fact space is more democratic. We are all important, and we try to just find connections. In math, you have this less democratic system in the sense that you have a axiom, derivation, this, that, you go down. So it's kind of like a very different system. So in physics, and this is related to the fact that in physics, we never think we're at the end of the story. We don't think this is the first important thing and everything follows. In physics, we are open to change. We are open to reformulating and saying perhaps that fact which we thought was not important is more important than the other fact that we thought was the other way. So we are open to reshuffling and finding what is more important. So that's one very important difference between mathematical way of thinking or mathematical methodology, mathematician's methodology, with a scientist methodology. Scientist is not trying to put axiomatic structure because that often is not as useful to discovering the next fact. It's not like we cannot be logical. Sometimes some
mathematicians think so.
sometimes jokingly tease us by saying, "Oh, you guys cannot think logically about this." No, it's not that. We know how to think logically. We know how to organize it, but it's not as useful in many questions. And we are open to reshuffling and redefining things so the order of what is fundamental changes. And that's the big difference.
Yeah, I see. Yeah, so that's a very interesting way to think about it. Usually when I'm asked about the difference between physics and mathematics, I try to answer in terms of the object we study. And obviously, object mathematicians study and object physicists study are different. The physicist studies things that exist in the actual nature, while mathematicians explore the Platonic world of logic. But somehow your answer is sort of try to explain the difference of the approach and thinking of physicists and mathematicians. And that's very interesting. And also, I think is reflected on your book. And so that's very interesting. So we talked about the mathematicians and physicists. So that naturally leads to another question posed by the audience, which is that, why did you want to become a physicist, or in particular theoretical physicist, in the context of in this audience? And maybe to connect to the previous discussion, rather than mathematicians. So you are, I mean, your mind is very mathematical, and you could have become mathematician too. And why did you choose to become physicist rather than mathematicians?
Okay, these are good questions. Actually, to begin with, I should say that I was not planning to become either a mathematician or a physicist when I started my undergraduate studies at MIT. I was planning to become electrical engineer or economics major. So that changed when I learned more and more about physics and math. I found that my love for physics and math is beyond something I can do anything about. It was far more. I was far more excited about physics and math. Now, why did I choose between one or the other?
Right.
Actually, when I was undergraduate, I had much easier time with mathematics than with physics. Mathematics was easy to follow. You open a book, it's clearly stated what are the assumptions, and then you prove. It's very clean, neat. You know, if it appeals to sense of neatness and elegance that the mathematics has. Physics, on the other hand, appeals not so much necessarily to the logical evolution of steps of ideas, but the reality around us, the beauty of the connection. You know, if you take a ball and you throw it that way, if you give it with this kick in this direction, where it will fall by just doing a simple math calculation is amazing. And that fact does not require any deep mathematics. But the very fact that there is something you see in your eye, with your eye vision, something is happening, and you're doing something in your mind about these equations, they are related, it's hard to explain why that's so exciting, but it is. And so I found I was in a tension that one aspect of me was liking the neatness and simplicity of steps in mathematics. On the other hand, another feature appealed to me, the physics part, where to me the physics was what was actually there. And we wanted to learn about what are we here for? Why are we alive? What was it before we were? What is it after we go? We wanted to connect ourselves, at least I felt I wanted to connect myself to a bigger piece of reality, just by learning a little more about what that reality is. Just understanding a little more, even though I know I would never understand the whole thing. I know that. I know a tiny little more understanding gives me this connection to reality, much bigger than the little tiny space I live in and the tiny time we live in. So it gives me a connection to give me a meaning to my life. And that, I felt, that to me was more valuable. And that was ultimately the reason I decided to go to study physics, despite the fact that I felt it requires much more energy for me. And it was much easier for me to do mathematics than physics. So I put my energy into that direction because I felt it is a connection with reality that I'm after.
How did you do experiment? How were you with experiment?
Oh, you mean with hands experiment in the laboratory? Don't ask. I was not good. I still am not good with hands.
Yeah, well, so same with me, I'm afraid. But indeed, so I understand. And in some sense, it's also the reason why I chose to study physics rather than mathematics. So yeah, it's kind of, I really appreciate and understand that. So I think we are sort of getting close to the end. So let me ask you a few things about your course at Harvard.
Yes.
So student mostly physics major, or what are the composition of your students?
Yeah, these are among the cream of the crop in terms of talent. These are freshmen who just entered Harvard, who maybe just a few weeks before just came from high school to college. So it's really just the beginning. And they are composed of, the smartest people who are interested in learning. And these could be students who participated in mathematics Olympiad, those who participated in physics Olympiad, or people who participated in neither one, but just smart people. And they're always extremely dynamic group of people talking with each other and so on. So one feature of my class was that it's a 2-hour class every week. And after the first hour, I would take a break for 10, 15 minutes, I put some snacks, and I leave the room. And what happens that 10, 15 minutes is where they learn. They interact with each other, and they bounce ideas about the puzzles I told them, and their own puzzles and their own discussions. And that's my aim. My aim is to try to trigger in them something which excites them. And I see that it's happening. So that 10 minutes, 15 minutes is the precious to me, to let them learn from each other and interact. And then I come. So indeed, the composition is the composition of interest. And it is not about requirements. It's a pass or fail course. Everybody passes. And the requirement is very light reading. And I give some of the class. Yes, the students can choose freshman seminars, and they rank with their top choices. And we select the students, and based on what they write about their own interest and how they have ranked what they are trying to do.
You know who they are, and then you choose students. So that's why you said they are cream of cream. I see.
Yes.
I see. That's very interesting. And have you tracked some of them? Have you followed up on them?
Well, many of them are becoming, some of them have already gotten PhD in physics.
Oh, okay. So they followed
Since I have been teaching this course more than 10 years now, I have already seen people who have already gone through that stage.
Okay.
So indeed, it's very rewarding to see the people. And some of them told me that puzzle course changed their attitude, and they decided to do physics related to that course. That when I hear that, I'm really delighted to hear that this had such an impact. But even if they didn't change their field, even if they did whatever they wanted, I think this idea to try to convey how scientists think about this to the public more generally is something which is valuable to me. I would be delighted if the book conveys that feeling to the people more broadly who are not necessarily scientists or not even interested in becoming scientists, but want to learn how scientific thinking is. These could be young people at high school or college, or people who are in all walks of life, studied, or even retired people who are interested in going back and kind of refreshing their mind about scientific thinking. So I would be very happy if this kind of thing triggers some thoughts and some pleasure about thinking about reality and the connection with mathematics.
I see. So I guess we are getting close, and so I have one final question. So you have been teaching this course for 10 years, and you published a book in 2000, which is 2 years ago, and I assume you have been still teaching this course.
Yes.
But in this book, you have disclosed the solution to the puzzle. Yes. So how have you been teaching this course?
Yes,
have you come up with new questions?
Good question. So first of all, yes, indeed, when I was trying to write this book and the solution, I was wondering whether I should put the solutions or not in the book. And part of it was exactly this, that I thought if I put the solutions in the book, then the students I wouldn't be able to teach the course because everybody has the solutions in the book. But then I thought about it. I said that, well, if I don't put the solutions, I cannot explain what I'm trying to learn from the puzzle.
And so there was the problems that are really hard,
So I had to I actually explained what the solution is so that what you learn from it is this or that. So I said it cannot be. I had to get the solution. So what I learned eventually was that, okay, the students are interested also to solve the puzzles like I am. When somebody gives you the puzzle, you don't want to see the solution. You want to do it yourself. These are those kind of people. Right. So I told them, look, please don't look at the book, and none of them do. And sometimes I even give the book for free to them. I said, these are the books, but please don't look at the solutions until we are done with the course. And they listen, and they enjoy it because they like puzzles. That's why they take the course. There's no other reason to take it.
Yeah, great. Yeah, so when I got this book during the pandemic, I tried very hard to solve every single problem without looking at the solution. And that was a lot of fun. Yeah, so thank you.
I'm impressed that you could do it. I couldn't solve all the puzzles myself. I now know them, but it's not easy to solve some of them.
So thank you so much. So do you have anything you want to say finally to the audience?
I want to say again that I have been extremely lucky and happy to be here in Japan. And I want to say that actually tomorrow I'm participating in a conference in honor of my friend, the renowned physicist who's so humble and sitting in front of me, Dr. Professor Hiroshi Uguri, who has made a great impact in string theory and high energy physics. We are celebrating in this conference the 60th birthday of Hiroshi and all his contributions to physics. And it's a great pleasure to be here in Japan to celebrate your birthday as well tomorrow.
Thank you very much, Cumrun, for your kind word. And also, thank you for coming to Japan to launch this book, but also to the conference starting tomorrow.